All right, we are going to talk about the rotation of rigid bodies. This set of PowerPoints I got from a different book, so the chapter number is not the same. I think it's chapter 10 in your book, but the title's the same. Rotation of rigid bodies. You can read all that at your own leisure. We're talking about things rotating around. Okay, so the first thing we're going to do is define our position. So we have some object that's rotating around, and we're going to let theta represent the amount of the rotation measured always in radians. So a delta theta would be a change in angular position. And we're going to take as our convention that a counterclockwise rotation is positive and a clockwise rotation is negative. Remember this is going to be pretty important later, that remember arc length is S equals R theta, where theta is your angle in radians. Well, a radian is defined as that special angle, so that the radius here will equal the length of this arc here. And it's pretty easy to show them because the circumference of a circle is 2 pi r. The number of radians in a circle must be 2 pi. So you have to rotate around this many, or this angle, about 6 times to make a complete circle. So by definition, an angle measured in radians is the length of the arc divided by the radius. So S equals R theta. This is going to come in useful later. Okay, we could define an average angular velocity measured in radians per second by doing a change in theta, an angular displacement divided by change in t. Now, this is a vector, and we're going to measure it as perpendicular to the surface here. So that's why we have this little z here. This follows the right-hand rule. If you point your thumb straight up the z-axis and curl your fingers around, your fingers will curl around this direction counterclockwise, and your thumb points straight up the z-axis. That's the direction of this angular velocity vector. So a positive omega here is when you're rotating around this direction. Negative would be rotating this direction. And of course, since that's a delta theta over a delta t, we could take the limit and get a derivative and get an instantaneous. Okay, that's what we just said. All right, so theta here might be a function of t, your angular position in terms of time. Take the derivative of that and you get your angular velocity, your instantaneous angular velocity. Sometimes we'll call that angular speed, angular velocity. They mean roughly the same thing, keeping in mind that this one's technically a vector. Here's the right-hand rule. Again, if we're rotating around like this, notice your fingers would have to curl around in this direction. So looking at it from above, that would be counterclockwise while your thumb points up using your right hand. If you point your thumb down, though, your fingers would curl around. Looking at it from above in the clockwise direction, that would be an angular velocity vector pointing down. Okay, so omega here, the vector points out of the plane in which you're rotating. That's positive angular velocity, that's negative angular velocity. Rotating counterclockwise, looking from above, rotating clockwise. Okay, then we could define an average angular acceleration as change in omega over change in t. Take the limit as delta t goes to 0, and we'll get an instantaneous Okay, I guess we don't have that there. We would get an instantaneous angular acceleration. Oh, there it is. That's what I was looking for. Okay, just like with regular velocity and acceleration, when those two objects point in the same direction, you're speeding up, and when they point in opposite directions, you're slowing down. Okay, now not all angular motion is constant acceleration. Like, alpha might be a function of time. You might have something that's speeding up at an increasing rate. So you might have alpha not be constant. But if alpha is constant, then these are our equations of motion for rotations. Notice they look exactly like the equations of motion for linear motion. So now instead of saying A for acceleration, we say alpha. Instead of saying V for velocity, we have omega for angular velocity. And instead of position being X or Y, our position is angular position, which is theta. Just like we almost always called X naught 0, our initial angle will almost always call 0. In fact, I can't think of a single time when this is not 0. So theta here will end up representing our total angular displacement. Write these equations down in your notes. You want these. We don't really ever use this one, just like we've never really used this one. You can write it down if you want, but we can get everything from these three. Okay, so how do we get from linear over to angular and back and forth? So we've got this object rotating around. It's rotating around at some angular speed omega in radians per second. Then imagine some point here, this point P, that's this distance r away from our center of our axis of rotation. How fast is that point traveling around the circle? Well, the distance it would travel would be the arc length, s equals r theta. So to get from angular velocity to linear velocity, it's the same idea. We multiply by r. We get s equals r theta, v equals r omega. S equals r theta, v equals r omega. To get from angular to linear, multiply by r. That's the distance it covered. That's how fast it's moving, literally through space. Okay, acceleration's a little different. We have two different kinds of accelerations. We have our angular acceleration. That's what's making us speed up or slow down. Then we have our radial or centripetal acceleration. That's what's keeping us on the circle. So the centripetal acceleration, same thing it always has been, v squared over r. That points toward the center of the circle. That keeps you on the circle. If you're on a merry-go-round and you're moving around and you feel that force pushing you toward the center, that's this guy. That's the radial or centripetal acceleration. Doesn't change your speed, it only changes your direction. Now, if your merry-go-round is speeding up, you're going faster and faster, then you have a tangential acceleration that comes from alpha. That's the angular acceleration. That changes your angular speed. That produces this tangential acceleration that changes your linear speed. And that always points tangential to the circle. This one changes your speed. This one changes your direction. And just like S and V, to get from angular over to linear, we multiply by R. So A is R alpha. And then this guy's the same thing we've always had. A radial, or centripetal, is V squared over R. But V is R omega. So we could plug in an R omega here. I think I didn't notice this before. There's a typo right here. This radial should be r squared omega, not r omega. So change that in your notes. Make sure you write that down properly. All right, remember, always use radians, not degrees. All of these equations we've been using only work in radians. A rotating object has kinetic energy, just like translational or linear kinetic energy is 1/2 mv squared. Rotational kinetic energy will be 1/2 I omega squared. Remember, omega is the angular version of v, so that fits right where a v would be. I here is called the moment of inertia. That's a measure of how hard it is to make something spin. That's the angular version of mass. All of our equations that we've had before that have an m in them, for angular versions will have an I instead. Okay. And the moment of inertia, this is the simplified version of it. For discrete masses, when you got a bunch of masses all tied together, the moment of inertia is each mass multiplied by the distance of that mass from your axis of rotation squared. Okay, we'll do some problems with this, and this will make sense. This is the discrete version. The more complicated, real calculus version is an integral. Units here are kilograms meters squared. Okay, so here's kind of an idea behind moment of inertia. It's a measure of how hard it is to get something to spin. Mass is a measure of how hard it is to get something to move in a straight line. Moment of inertia is the rotational mass. It's how hard it is to get it to spin. So imagine we were trying to spin this little device here. Because these guys here are close in, it's relatively easy to spin. But if we were to move these masses out, it would be harder to spin. The further your masses are away from the center, the axis of rotation, the harder it is to spin. When everything's close to the middle or everything's equally spread out, everything's uniform, it's easier to spin. When everything's really far away, it's harder to spin. So they're making this point here that hummingbirds are small. They have a small moment of inertia, so they can rotate their wings really quickly. It's really easy. But a big bird's got a big wing. There's a lot more mass, and the mass is further away from the axis of rotation here at the shoulder. So it's hard for it to move and rotate its wings. That's why it flaps much slower. We got a whole table of moments of inertia. We're actually going to derive these two in a video. These are just things you look up. The parallel axis theorem is a shortcut for getting a new moment of inertia from an old one. So this says if you want your new moment of inertia, take your old one at the center of mass, add to that the mass times the distance you moved your axis squared. So here's the center of mass. If I had an axis of rotation right here, meaning I want to rotate the bat around this axis. Somebody's already found that moment of inertia for me. I know that number. Now I want to rotate it down here. Or I'm going to take the old moment, add on the total mass of the bat plus this distance I moved the axis squared. This is the real version of moment of inertia for non-discrete masses, for masses that are spread out. We're actually going to use this to do a calculation. It's an integral.